Welcome to lecture 8 for Chem 103 on Wednesday, the 23rd of March. You will have seen that I've started the recording button. This morning, we left off with, we were talking about exchange of heat between a system and its surroundings. And you can almost think about that if I take this nice cup of coffee with the frozen emblems on, which is from one of my children. So they'll probably be upset that I drank coffee out of it. But I'm actually now exchanging heat between the surroundings, which is the coffee cup, and my system, as long as I define myself as the system. So what we were talking about was the exothermic and endothermic processes. One of the things that is a really good example of an exothermic reaction is the heat pack. You might know them, they come in various shapes and you usually have to whack them or click them, as we're going to see, and then they start feeling hot. So if you actually open one of these, if you look at this video, so you can see here, it's on my desk and I come in with a little prick. I'll give it just disturb the system. And you see this really nice crystallization happening inside. And once that crystallization is complete, then you get this sort of phase change. So there's all of this work is going on. So inside it, you really have an unstable sodium acetate solution. You can also watch this video online if there's the YouTube link there from probably from a few years ago. So the pack gets warm. If you turn the audio on, you can actually hear like, oh yeah, that's nice and hot. And you can see it's formed this solid. These packs aren't very large, but it forms this really nice solid material and this crystallization that occurs. So that's a really good practical example of an exothermic reaction where heat is being released to the surroundings. Whereas in the case of my coffee, I'm taking up heat from the surroundings. So if we look at this, you know, and actually look at the reaction, actually one of the things that we'll look at later on, you can also use this crystallization process to quantify how a reaction is proceeding and actually do some kinetics on it. Kinetics is the study of how fast things are reacting. But if we look at this, we go from the full-on liquid state, even though it's a cool liquid, it's an unstable liquid. And then when we disturb the liquid, this crystallization reaction occurs. So we go from the liquid state to the crystal state. And that actually, because we had to cool this down to form this, not because we had to cool this down, but we cool this down, and then we start off with this nice, usually room temperature material, and then we end up with something, not a material, it's a liquid inside a plastic bag, and then we end up with this hot sort of material that you can then use to warm yourself. They're really, really nice to use. They're also reusable. So the one that we just had, there is nothing I can do to go from the crystal state back to the liquid state with this. This is not really reusable. That's why the arrow is in one direction. The reaction, if we define this as a reaction, goes from the liquid state, turns into crystals, and it's not possible to turn them back. You can actually buy reusable heat packs. There's a reference there where I got this information from, and it's usually, it has some form of sodium acetate in there, and then it's got this sturdy plastic bit, and you can then, there's a question, what is heat pack? Well, a heat pack is a what's it called, is something that increases its temperature can't see what I'm typing now. Increases its temperature when you disturb it. See the previous, as discussed in the previous slides, on the previous slides, and these few slides. So in it, you would have sodium acetate. There's actually a clicker. So I don't know if you can see this, but if you can't see this properly, then go and look on this reference. And it's something you just click, and then you get that same thing happening. You get this solution then goes to the crystals. And here's the sodium acetate. So we've got sodium cation with the acetate, which is a carbon with a double bonded oxygen. A single oxygen, there's a negative charge there. There's a second carbon attached with three hydrogens. And what happens is, so you go, so this is what the hot pack will do. It goes from the liquid state to the crystal state. You activate this reaction by disturbing it. So you saw me beforehand, I use this prick, this pin prick, but you can also do this with this metal thing. And then you go from cool till about, according to the information, 54 centigrade. So nice and warm, but not hot enough to burn yourself, which is obviously good. You can actually reuse them by sticking this sturdy material in boiling water. So what you're doing there is you're putting energy back into it. So energy is being absorbed then by the system. Once you've turned it back into the liquid, then you need to allow it to cool, obviously, otherwise it's not going to be a hot pack. And then you can reuse this again. So in all of this, what we're obeying here is our first law of thermodynamics. We're not really creating energy. The hot pack doesn't create energy. It releases, it changes, it transfers energy from the crystallization process, releases heat. In order to go back, we have to take the crystals and turn them back into the liquid state. The reason why you can't do that with the first hot pack that I showed is that probably the plastic around it isn't really useful in doing that. The other thing, of course, is we compromise the plastic by putting a pinprick on. And when you usually use these single-use hot packs, you, as I said, you whack it and you break the plastic and it immediately turns hot. So in order to reverse that is much harder. But these ones, they actually have these really sturdy plastic around it, and they have something in there that you can clip and click and to disturb the liquid state. But the important thing to realize here is it is a transfer of energy. The heat pack does not create energy. We're simply transferring this heat. So if we then look at our diagram again, the reusable, we go from liquid to crystal. So in one case, we're doing work. So we click, so we do work on the system. That turns it from a cool to the hot state. Then we add heat to it and we go back to its initial state. So we use boiling water and then we allow that to cool. So there was a question this morning, what are examples of things that are not state functions? So heat and work are not state functions. So if we look at this example from the textbook, if I have a battery and I drain the battery by hooking it up to a coil and converting the electrical energy to heat, we go from the charged battery to the discharged battery where we have energy is lost by the battery. So that's one way of discharging it, the internal energy. Or I can hook it up to a fan. It has to be probably pretty powerful, or it can be just be a small fan. And then the fan will do some work. It will rotate the blades around and provide you with cool air, or will move the air around. And then it will also give up some heat because the fan will not be completely efficient. So in both cases, we go from a charged battery to a discharged battery. So in terms of delta E, the change in internal energy, where E is a state function, it doesn't really matter on the path that we take. The change in energy is the same whether we do it all in heat or whether we do it partially in heat and partially in work. So that means that Q and W, they're not state functions, because they are, there we actually do, those depend on the path that you follow. So we can also look at work. In most of the cases, when you look at these textbooks, they'll talk about work is like done with mechanical work. You saw the example that I showed this morning of me dropping a weight on the fin. That's doing mechanical work. A lot of these examples that are being used in textbooks are these pistons, where you have some form of initial state that's usually in gas that is enclosed in it, and then by changing either a reaction or some other mechanical work, you get a volume change. So you see here the initial state, and then there's the final state where you have a change in the height, which gives you your volume change. So usually we can then define work as equal to minus the pressure times the difference in volume. So in this case, the pressure is related to force over area, which is the general definition of pressure. So in the case of this piston, it would be the area of the piston and then whatever force there is working on that, which can be exerted to pressure. And that's how a lot of it in this case is related to work for in the sense of what we're talking about in the books. This is another version of doing mechanical work. This is my Christmas video from a couple of years ago. You can see I am pretty pleased with the result. Also noticed our beautiful Brett has his Christmas jumper on, I have my Christmas t-shirt on. And I should also point out that what we're doing here isn't just pure destruction, because we're actually looking at the transfer of load as we're doing work on this surfboard. So the surfboard has, there's a sensor, this bit here on this wood splitter, and then there is also a sensor here on the board. So by putting in mechanical work, we can look at how does load transfer. But in essence, we're doing mechanical work. There may also be a little bit of heat generated as we're doing this impact. And I should point out, in case this is disturbing for you, this surfboard was already broken. It's missing part of the nose. You can also see it's creased here in the middle. And it's so when something breaks, I reuse it. But the point here is we're doing mechanical work on a system, and that mechanical work, you know, that what Brett is doing, it is obviously costing him energy to do this, but there might also be a transfer of energy. So from the mechanical energy, from the impact energy, there'd be some slight heat being generated as well. So one way of that this is being measured, how you do the work, is if you have this piston system. And in particular here, the work is defined as negative because the system is doing the work. You can have, for example, you can have some zinc into hydrochloric acid. I think this was one of the ones that we did in the lab. If you add zinc, you then get the formation of some hydrogen gas. So if we add zinc in here, you close the system off. So we are again working with an enclosed system. You let the reaction proceed. There will be some bubbles happening that increases the pressure inside the system. And if the piston can freely move, then as a result of the change in the volume, the pressure, you can work out what your work is done on the system. And that sort of takes us to the definition of another thermodynamic entity, which is called enthalpy. And this usually works on if we assume that we are working at constant pressure. So if you think back of the laboratories that we did, we usually, in our labs, the pressure doesn't really change. So that means that the only work that then occurs is due to this pressure volume consideration. So then what that allows us to do, by assuming we're going to be at constant pressure, that means that we can measure the heat flow, or we can think of the heat flow by measuring something that is called the enthalpy, and the enthalpy is generally designated as H. If we then look at the definition of that, then there's a question there, what is E? So E is what we've been talking about all day so far. E is the internal energy, which is written, if you read what it says on the screen on it, it says enthalpy is the internal energy plus the product of pressure and volume. So H for enthalpy is equal E, which is the internal energy, plus the product of pressure and volume. So there's another question, isn't H enthalpy? Yes, that is correct. So H.
So is H and E the same? Like, are they both enthalpy?
No, H is the enthalpy. H is the internal energy plus the product of pressure and volume. So H and E are not the same. They differ by the value of P times V.
Okay, yeah.
So if we then continue and we go and look at what happens when we do constant pressure, then the change in enthalpy is usually given by the change in the internal energy plus the product of P and V, which, if we assume constant pressure, then this equation here reduces to delta H equals delta E plus P times delta V. If we are not at constant pressure, then we would also have a delta P times V product in here. But if we are assuming that what we're doing in the normal world is always at constant pressure, then this is the equation that we can use for the change in enthalpy. We can then do a bit of substitution, because we obviously know that what delta H is. Delta H is the product of the heat plus work. So delta H is Q plus W. We also know that we can define minus P times the change in volume as work. So if we substitute that all in, we know that work cancels out. So so that means that delta H is then equal to the heat. So that means that as long as we are at constant pressure, the change in enthalpy is then either the heat that we gain or the heat that we lose. And then we can look again back at our endothermic and exothermic processes. So a process what is endothermic, where you gain heat, that means that our delta H is generally positive. So we're gaining something, so the change in enthalpy is positive. If we're losing something, so if energy is coming out, then that process, then that leads us to define that delta H is a negative value. So delta H will be smaller than 0 and we lose heat out of the system. Or what is written here at the bottom, it says that delta H is really the amount of heat that flows into or out, obviously, can go in and can go out, under the constant pressure, which is what we're looking at. So we can start applying this and use this concept of enthalpy to our reactions. So we can say that the change in enthalpy is equal to the enthalpy of the products minus the enthalpy of the reactants. And then we can start looking and we can make these little diagrams. For example, we can plot enthalpy on the y-axis And then over here, we got the process of the burning of methane. CH4 gas plus oxygen, which is balanced, gives us carbon dioxide plus 2 water molecules. So this is balanced. So we know that if we burn this, we release heat because it's a burning reaction. So we have energy loss. If I go back one slide, you will see we have a heat loss. So heat is coming out when we do this. Or we have, if we want to turn our carbon dioxide plus water back into the original products, we'll have to put a lot of energy. We have to put the same amount of energy in to go back. So the change in enthalpy is then, as it says, the difference between the products and the reactants. So this enthalpy level here and this enthalpy level at the bottom, which is final and initial stage. So that quantity that we just looked at, that is also referred to as the heat of the reaction or enthalpy of reaction. And you can have, this is actually quite fun to do, but I don't think we're allowed to do these things anymore, but you can do an explosion. So for example, you can light up hydrogen and oxygen. You'll notice that this is a balanced equation. It turns into water vapor. We have an absolute violent reaction. As you can see in the picture here, there's a bit of an explosion. If you think back of what we did with the ethanol whoosh rocket, that was also some explosion was happening that released gas that allowed this thing to, this whoosh rocket to move forward. So we get some form of violent reaction happening. The oxygens, so obviously the bonds in the oxygens have to be broken, the bonds in the hydrogens have to be broken, and then there's also a formation of bonds again to form water. And that's again an exothermic reaction. Here we got the balanced equation, 2 hydrogens combined with 1 oxygen to give 2 water vapor. And as we are going down, that means our delta H is smaller than 0, which means that it releases energy to the surroundings. So that's generally the case. If you see an explosion, you will know that it's going to be hot in most cases. So we know then, if we talk about what these properties are, the enthalpy change is obviously, if it will be the same in size or magnitude, but it will have a different sign if it's the reverse reaction. And generally we know that the change for a reaction depends on what the states of the reactants and the products is in. So if we do this, and this was an experiment that you may have done if you've done high school chemistry, you may have already done something like this, but this is one of the simplest ways that you can measure. And by the way, this is also, if you look here, you got 2 styrofoam cups nest together. So the outside one is used pretty much to insulate the other one. If you get, for example, I drink long black coffees, and sometimes I ask for extra hot, they usually put them in an arrangement like this, because if you put 2 styrofoams together, you very nicely, or to a certain extent, you isolate the heat from the inside one from the outside one, so you can actually hold it in your hand. Whereas if you have a single cup, it becomes a lot harder. But this arrangement is actually one of the simplest way of measuring heat, because what you can do, you can have a liquid inside 2 styrofoam cups. You need some form of material there with a low heat transfer. You've got some water in there, and then you've got a reaction mixture in there. So if you also put a thermometer in there, you can measure what is called calorimetry. So you can measure the heat flow. So you can measure the flow of heat from the reaction that then heats up the water. Once we know what the increase in temperature is, we can actually calculate that, because we know how much heat is required to raise the temperature of water by 1 degree. And that's something what is known as the heat capacity. So, and there's various ones available. Water is one that we can use a lot. So it has a specific heat capacity of 4.18 joules per gram per Kelvin. That means if you want to raise the temperature of water by 1 degree, so 1 gram of water by 1 degree, either centigrade or Kelvin, you need 4.18 joules. Measure, so there's a message there that is asking, do we measure the temperature of the liquid or the entire system? So we measure the temperature of the liquid. So if I go back, you can see that the thermometer is inside the liquid. So that's what we're measuring. That is a representation of our system temperature. There will be, of course, this is not a perfect isolating system. So it's an approximation of the heat that you can get. If you want to do this perfectly, you have to make sure that nothing can come in from the outside. So if I go back to what I was saying, if we want to raise the temperature, let's say you have 1 gram of water, which would be 1 milliliter of water, and you want to raise that from a temperature of 14.5 degrees to 15.5 degrees, you need 4.18 joules of heat. And you can see here other materials. So water actually needs quite a lot of energy compared to methane, carbon dioxide, or even if you look at iron, doesn't actually need a lot of heat. That's why metals generally, if you leave them in the sun, they get hot much faster compared to if you would have, say, some water in the sun, because metals here don't need a lot of heat to raise their temperature. They're very good heat conductors, whereas water takes a bit more time to release the heat. And that actually also comes back to our ocean, of course. So it can be a really hot day, but if it's just after, let's say we had a cold flow going through, the air temperature can be hot, but it takes a lot more time for the water temperature to follow suit. And that has to do with this specific heat, because you need to put a lot of heat into the system. Is this why, so there's a question, is this why mercury is used in temperature gauges because of its specific heat due to its sensitivity? I don't actually know that, but Cohen, if you're, can you just Google that and pop the answer back in the chat? I don't know if that's the reason why, because mercury is actually very, very quickly. So it might actually have something to do with the expansion, but I'm not entirely sure. If you have time, can you Google it and put it in here? Otherwise, I'll cover it. I'll just make a note on and make sure that I cover it next time. So if we do this, so if we go back to our calorimeter, we can now carry out reactions, and we can use the raising of the temperature of water to actually calculate what our delta H is. So we know, so let's say the heat transferred in the solution, so that would be Q of the solution that we have. If we know what the change in temperature is, which we can measure before and after the reaction, then we know how much water we've got in there. And then we know what the specific heat is, which is this value CS. So we can then work out what the enthalpy is in this way. So there are obviously, this is just an approximation of what you can do. There are very, very sophisticated instruments available that allow you to do this. Calorimetry is a very well-established field of science. Mercury is the only one that's used in thermometer because it has a high coefficient of expansion. So let me just put that in the message to everyone. So the question was, is mercury being used because of its heat capacity? So the answer is, according to Google, is that mercury is the only one, and thank you, Cohen, is the only one in the liquid state at room temperature. So only one must be the only metal in liquid state at room temperature and it's used in thermometers because it has a high coefficient of expansion. What that means is if you heat it or cool it, it either contracts or expands really fast, which means that you can use it to have the mercury levels coming up and down. It's also not very good to use because whenever we used to have mercury thermometers in the labs, if something would break, mercury is not very good for you. If you have a chance to look at what the safety or what it says about mercury, I think it's probably carcinogenic. So there's a question, since only the change in temperature is used, not temperature, does it matter? Does it matter what Celsius or Kelvin? So Celsius, let me just, and then there's the second question, which I'll answer next. So Celsius and Kelvin work on the same scale, so increments. So they, what that means is, so yes is the answer on that. So change in Kelvin is the same as change in Celsius because they both work on increments of 1. The next question is, could you please repeat what CS and M sol is in this equation? So CS is specific heat in this case. So that's 4.18 for water. And M sol, excuse me, that is the volume of water converted to mass. So for example, 200 milliliters equals 200 grams. Was that clarified? Cool, thank you. So what I said before is there are obviously way more sophisticated ones. These ones I refer to as bombs for some reason, because they have, if you look, you have a larger chamber that has a thermometer involved. It's an insulated container, so it's a bit more high quality than the 2 styrene cups. And in that, so the whole thing is immersed in water, and in there you've got a reaction chamber where you can then carry out the reaction. The principle is in essence the same. What is being measured here is the increase in temperature of the solvent. It's just that there is less heat probably being lost to the surroundings, but also less heat coming in if you're working at different temperatures. So, and again, the word here to keep in mind is that this is always approximation. So we are calculating, we are approximating the enthalpy change for these reactions, because we are allowing heat transfer. So these heat transfer processes aren't probably fully accurate, but they're getting more accurate as you go to this arrangement compared to what we had with the two with the two styrene cups. Sorry, that's the word I was using for. I was trying to multitask there and read a message and talk at the same time. So one of the things that we talk about here, of course, is that because we now have a constant volume, and that's where you got to look back at the equations, we're actually measuring the change in internal energy, right? Because so enthalpy is internal energy plus pressure times volume. So if we have a constant volume as well as a constant pressure, then the whole delta PV doesn't come into play anymore, and delta H is just equal to delta E. If you don't know what I'm talking about, let me just go back a couple of slides and I'll show you what I actually mean. Where is that equation? Sorry for flicking back. We'll get there eventually. delta H. Here we go. So if there is no volume change, so if we're already assuming we're working at constant pressure and there's no volume change, then this here becomes 0. Delta V is equal 0. And that actually means that what we're measuring in terms of the delta H is also the change in the internal energy rather than just Q. So bear that in mind. Well, actually, no, you don't have to bear that in mind. I'm sorry for flipping forward again. We do know that usually that's pretty small anyway. So that brings us to another law. So we already saw the first law of thermodynamics. Now we're going to see another law, which means if you carry out a reaction in a number of steps, then the overall, the change in enthalpy of the overall reaction is just the sum of the enthalpy changes for the individual steps. And it also means that the number of steps is not really important. It's only really the final and the initial steps. So let me illustrate that with an example. If I have the enthalpy here and I'm going to burn my methane, for the change in enthalpy for burning methane and converting it to carbon dioxide gas and water, it doesn't matter if the reaction goes in one go or if there is an intermediate step where we first form carbon monoxide and then form carbon dioxide. The end result is the same. It doesn't matter how many steps we take. So in order, if we have this reaction here on the right-hand side where we have a carbon monoxide step first, the overall enthalpy will be the sum of delta H2, which is that initial step for forming carbon monoxide, and then the end step, which is delta H3, which is the formation or the conversion of carbon monoxide and the remaining oxygen into this carbon dioxide step here. So again, it's not really important what happens in between. It's only the end, the initial and the end state. And that's also because H is obviously a state function. A state function means we're just interested in the initial and the final steps. If you're wondering who Mr. Hess was, he came originally from Switzerland. He was a medical doctor and he did chemistry in his free time, which is yet another example of somebody that where chemistry wasn't really his main occupation. His main goal was to practice medicine and to help people in general. So it's another interesting example around that time where people did something on the side and made some really amazing discoveries. We should also define what we mean by enthalpy of formation, which has the symbol delta HF, where F obviously stands for formation. There's another question. For the second term, which is PV, is the same. Is it the same as delta M, since mass is a form of energy? I don't know that, Ahmed. I don't know for sure, because energy in that case is actually related to the speed of light, if I'm not mistaken there. So I don't know the answer of that question. The enthalpy of formation is defined as the change in the reaction if you make a compound from the individual elements. So if we are going to make something, we have to look at what the changes in the enthalpy is of the molecules or compounds that we have to break and then rejoin again in a chemical reaction. If you remember, most chemical reactions will involve the making and breaking of bonds. And we can have these enthalpies of formations. You also got to bear in mind that they are usually at a particular temperature. So standard condition in this case is 25 degrees centigrade, not 0 degree centigrade. That is a very big mosquito in my office. Sorry. And it's also at 1 atmosphere pressure. So we can have these standard enthalpies of formation. If you look, let's pick up, where's our water? So water, the enthalpy of formation is 285, water vapor is a little bit less. We've also got methane, which is 74, methanol. So you got all kinds of different materials in there that deal with the formation of enthalpy of formation. And we can calculate these things. So if we're going to burn C3H8 and we have to apply some oxygens for that, and we have a nice nice balanced equation that gives us some carbon dioxides and water, we can think of this occurring in 3 steps. So here we've got, for example, so it would be obviously if you have C3H8 or propane, if you're going to decompose that into the elements, so you have to split this molecule up in order to then attach and have bonds formed with the oxygens, and also to have the hydrogens combined with the oxygen, and the oxygen molecules have to be broken up as well. So you can think of this as a number of steps. So for example, the first step could be where propane decomposes into graphite plus hydrogen gas. So if we look here, we get, that could be our decomposition. So we have propane, it goes to graphite plus water, and there's still obviously the oxygen present because we haven't used that yet. In the second step, there's actually, if I go to acetylene, that could actually have a similar side step evolving, where the first carbon, the alkene, which is an alkene is usually carbons and hydrogens, that could actually fall apart into some graphite plus hydrogen, plus obviously also the oxygen, because if we haven't used the oxygen, then it's still present. So if I go back to propane, in a second step, we can have the formation of carbon dioxide. So we can have the graphite combining with the oxygens. We've still got some oxygens left because we haven't used them all in the formation of our hydrogens, because this is only goes from graphite to carbon dioxide. We haven't formed our water yet. So we get a second type of reaction. In the final step, whatever is left in the hydrogens and the oxygens then combine to water. So this is an alternative route where we can go decomposition into elements, formation of carbon dioxide, formation of water. Or you can also obviously just go in one go. So your propane combines with oxygen and you get your products. So if we look at all these 3 steps, and this is something that you need to do and goes back to what we were talking about before, which is you've also got to think about and look at that you've always got your balanced equations, so that all the carbons and all the hydrogens, that they always match up. And if we do that, we add up everything that's on the left, and we add up everything that is on the right, and make sure that we cancel out anything that is on the reactant side, but also on the product side. And now we can use Hess's law, which in a mathematical way is written as follows. So it is the change in enthalpy is equal, and this is a summation sign, times you use the stoichiometry in this case with the delta H of the products, and then you subtract all the enthalpies of it, taking into account the stoichiometry of the reactants. And then it becomes a simple addition. So if we do this for the propane that we just looked at, so we got to take the reactants. So we've got our carbon dioxide plus our waters. And then from that, we have to subtract the propane and 5 times the oxygens. And that gives us our final value. You can do similar things in terms of enthalpy with formation. You can also talk about bond enthalpies, because it obviously requires heat to break up a bond. So nitrogen or methane, you have to split prize these hydrogens away from the carbons. And the bond enthalpy is always considered as positive, because it really takes energy to open up a molecule. It's not easy when you have a chemical, or what is sometimes called a physical bond, a covalent bond. It's very hard to break these open. So you got to put energy into it. So if you want to take away a hydrogen from a carbon, you need about 400 kilojoules per mole. You also notice that if you have a material, if you have, sorry, not a material, if you have two carbons and they actually have a double bond instead of a single bond, a double bond means they're more tightly compacted together. We obviously need a lot more energy. You can see the same thing for carbon, where you have an oxygen has a single bond versus carbon that has a double bonded oxygen onto it. You need almost twice the amount of energy. The same if you want to just split open an oxygen, it is a lot less required than if you have oxygens bonded together with a double bond. So this also obviously means that the greater the bond enthalpy, the stronger that the bond is being formed. And I'm noticing that we're almost at the end. So if we want to look at what happens when we do reactions, then we can do the same thing as that we did with the formation. We need to look at what are the enthalpies of the bonds that are being broken, and we have to subtract that with the enthalpies of the bonds being formed. I don't know what I've got left in slides, and maybe this will be the last slide. Let me just quickly check what I've got left to do. Yeah, that's just energy. So I can probably leave, I'll do this slide and then I'll leave the rest, which has to do with energy or foods. I'll leave that for you to read yourself, so that next week we can start freshly on thermodynamics. So if we know the enthalpies, we can also talk about whether reactions are going to be endothermic or exothermic. So if we have methane and we have chlorine, it forms, we need to break some bonds, then we need to make some bonds. And if we look in the energy diagram, you'll see that there is energy being released. So that means that we can calculate what our endothermic and exothermic reactions are. So I am mindful of time. Since it's 20 past 1, I'm going to stop here. Thank you very much for tuning in. Next week is workshop number 2. I know that some of the peer assessment of workshop number 1 is going on. There's also post labs going on, so keep an eye on what you need to complete. Thanks very much, everybody. It's still not raining where I am. There was actually a spark of sunshine, so make sure you get up, walk around, and I'll see you next week. Take care.